Greetings. In this clip, we're going to talk about the reorder point. This is a fundamental component, one of the two most important parameters of a continuous review inventory system, which operates as follows. You reorder when the inventory reaches the reorder point, and the quantity that you order is typically the economic order quantity. So it's those two numbers that are essential, those two parameters that need to be specified: the economic order size and the reorder point. I should note, if I just go back to a previous slide, what the difficulties are with the economic order quantity model. When you're placing this order, it takes some time, which they call the delivery lead time, denoted by L, to actually receive the order once the order is placed. And it's during this period that you're waiting for that order to come in that you're exposed to stock out risk. What you need to do is to set the reorder point so that you cover demand that's going to materialize during the delivery lead time, which could be, a couple of days, even hours, but on up to a couple of weeks, or even months. You need to be, have enough inventory to cover that average demand. And in addition, some safety stock. And the safety stock is addressing variability in that delivery lead time. It could be delays in customs or, from logistics providers, in addition to changes in the demand during that period of time. All right, so letting L denote the delivery lead time, D, the demand rate per period, let's say per day, and sigma sub L is the standard deviation of demand during the delivery lead time. We're able to specify the optimal reorder point. And it is D times L. This is the average demand during delivery. So the length of the delivery period is L, and D is just the demand on each of those days or periods. And then the safety stock is a certain number of standard deviations that gets added to that as sort of backup inventory to address the variabilities that occur in both time of delivery and demand during the delivery lead time. So sigma sub L is equal to daily standard deviation of daily demand times the square root of L. If you might be given sigma sub L, but it's probably more likely that you know the standard deviation of daily demand. So for example, if the lead time is 5 days, then sigma sub D would be the standard deviation of daily demand, and sigma sub L would be the standard deviation of 5-day demand. We specify or we calculate Z based on the kind of lead time service level that we're looking to maintain. And basically what this amounts to is a statement of the probability that you're not going to stock out while you're waiting for a delivery to come in. We call that the LTSL, the lead time service level. It could be in the 90s, it could be lower. You adjust it to whatever you need. And we're able to calculate, once we've specified a lead time service level, we can go ahead and calculate Z using the Excel formula norm.inv LTSL 0,1. So this is typically going to be, some value, maybe 1.6, 2.5 in that ballpark, a certain number of standard deviations. So let's see this at work. We had an office supply store example for our work with EOQ. We're going to require a lead time service level of 95% in our calculations. We're saying that it takes 2 days to receive the paper once we've placed the order. So L is equal to 2. And then the standard deviation of daily demand is 15 boxes of paper. So sigma sub D is 15. So what I need to do is I need to figure out the standard deviation of 2-day demand, and that is 21.2. And all I need to do is just to take the standard deviation of daily demand, sigma sub D, and multiply it by the square root of 2. We know that D is equal to 40 from our earlier work in the EOQ example. And because we want a lead time service level of 95%, I'm able to calculate that we need a Z value of 1.645. So then our reorder point is, the demand that's going to occur while we're waiting for an order to come in. It's 2 days, and daily demand is 40 per day. So we need 80 boxes to cover those 2 days on average while we're waiting for the order to come in. And in addition, we're going to multiply, create a safety stock cushion to just cover variabilities, and that's Z times sigma sub L. So, 1.6 times that's 21. And ultimately, what we need is about 115 boxes to order when the inventory reaches the value of 115 boxes remaining. So in summary then, putting together our ERQ example, which gets us the order size and this reorder point analysis, the way our optimal continuous review inventory system would work would be to order 204 boxes of copier paper whenever the inventory level reaches 115. And the annual order and holding cost of this system is about $6,119 a year. As we noted earlier, ordering 200 boxes every time is not going to change the numbers very much. But the key thing here in this clip is that we've added the reorder point.